Something crossed into our solar system on July 1st, 2025. It came from outside, way outside. A frozen rock the size of a small mountain, flying at 152,000 miles per hour, straight toward our sun. Then NASA went quiet. Telescopes went blind. Databases stopped updating. And millions of people online asked the same question: what are they hiding? Today, we follow this visitor from its detection in a Chilean desert, past Mars, through the sun's fire, and out into the dark it came from. A green, glowing comet, a signal from another star, and a mystery that scientists still cannot fully explain. If you enjoy this journey, like and subscribe. You won't want to miss what's coming. Let's begin. The night of July 1, 2025 started like any other at the Asteroid Terrestrial Impact Last Alert System station in Rio Hurtado, Chile. Robotic telescopes swept the sky automatically. No humans sat at the controls. The system just scanned, photographed, and compared, over and over, all night. Then a flag went up. The software spotted a point of light moving across the sky, moving fast, faster than anything local. The system had been built to catch asteroids heading toward Earth. It had caught thousands of them, but this one moved differently. The angle was wrong. The speed was wrong. Everything about it was wrong for something that belonged to our solar system. An astronomer reviewed the alert the next morning. The object was plunging inward from the direction of the constellation Sagittarius, far above the flat plane where our planets orbit. Local asteroids and comets travel in that plane, like cars on a highway. This thing came from above, diving in at a steep angle, like something dropped from a height we had never measured. The astronomer pulled up older sky survey images to check for earlier sightings. And there it was. Faint, almost invisible. But there. A team dug through archived images and found the object had actually been photographed as far back as June 14th, 2 weeks earlier. It had been sitting in a database, unseen, waiting. That discovery sent a quiet alarm through the astronomical community. If the automated system had missed it for 2 weeks, what else had slipped through? Within 48 hours, multiple observatories around the world turned their instruments toward the same patch of sky. They confirmed what the Chilean telescope had flagged. The object was real, it was big, and it was coming in fast. Scientists immediately ran calculations on its path. That was when everything changed. To understand what they found, picture the way a ball on a string moves when you spin it around your hand. That circular path is an orbit. Every planet, every local asteroid, every comet born in our solar system moves in some version of that path, curving, looping, coming back around. Gravity keeps them tethered. This object followed no such loop. Its path was a straight, open curve, the kind that comes from somewhere else, swings around a gravitational anchor, and keeps going without ever turning back. In math, that shape is called a hyperbola, and an object moving on a hyperbolic path has only one origin: outside. The international community moved fast. The International Astronomical Union officially designated the object on July 3rd. It became only the third confirmed interstellar visitor in recorded human history. Scientists gave it the name 3I Atlas, using I to mark it as interstellar, the same way the first two visitors had been marked before it. 2 weeks passed between its first captured image and its official detection. 2 weeks where this frozen messenger from another star drifted silently through archived data, unnoticed. That detail stuck with the scientists who found it. If this one nearly slipped past, earlier visitors might have done exactly that, passing through without anyone ever knowing. The comet was inside our solar system now, getting closer, and the telescopes that found it were only just beginning to understand what they were looking at, because the speed of this object was unlike anything they had prepared for. Speed is the key. That is how astronomers knew. Every object born inside our solar system, every planet, every moon, every rock in the asteroid belt, moves at a speed that our sun's gravity can control. The Sun is massive. Its gravitational pull reaches billions of miles in every direction. Anything born here, or captured here long ago, moves fast enough to travel but slow enough to stay. Gravity and speed balance out into an orbit. When an object moves too fast, that balance breaks. The Sun's gravity pulls on it, curves its path, but cannot hold it. The object swings around the Sun like a skateboarder hitting a half pipe, then launches back out into space. That is exactly what this comet did. Scientists measure this with a value called orbital eccentricity. A perfect circle has an eccentricity of 0. An ellipse, the stretched oval shape that planets travel in, has an eccentricity between 0 and 1. Any object with an eccentricity above 1 is on a hyperbolic path. The Sun cannot keep it, and this comet's eccentricity was measured at well above 1. That number alone confirmed it. The comet was a visitor. It did not belong here. To double-check, scientists ran the math backward. They took the object's current speed and direction and calculated where it came from. This is like watching a ball roll across a table and figuring out who threw it. The math pointed outward past our solar system, toward the general direction of the constellation Sagittarius. Sagittarius is not a single star. It is a direction in the sky that contains millions of stars, including the dense center of our galaxy. Scientists cannot yet pinpoint exactly which star system this comet came from. The galactic center is crowded with gravitational forces, and millions of years of travel have bent and shifted the comet's path too many times to trace back to a single source. But the direction was enough. The speed was enough. The eccentricity was enough. The team also confirmed the object by cross-referencing its position with data from multiple independent observatories. The Hubble Space Telescope, the world's most powerful optical observatory in orbit, swung its lens toward the incoming object. Ground-based telescopes in Hawaii, the Canary Islands, and South America all independently measured the same values. Every single one agreed. This was the third time in human history that scientists had made this call. The first was Oumuamua, detected in 2017, a cigar-shaped object with no visible tail that baffled scientists with its strange acceleration. The second was Borisov, detected in 2019, a more conventional comet that scientists could study more easily. Both entered, swept through, and exited our solar system without slowing down. Now a third visitor had arrived, bigger, faster, and far more active than the first two. Each time one of these objects crosses through, scientists get a tiny window to study something that formed around a completely different star, in a completely different part of the galaxy, billions of years ago. The chemistry locked inside these visitors carries information about worlds that no human telescope has ever seen up close. But before scientists could study this comet's chemistry, they needed to understand something even more striking about it. Its size was far beyond what anyone expected. Imagine throwing a baseball so hard it never comes back down. On Earth, every ball you throw eventually curves back to the ground. Gravity wins. But if you could somehow throw that ball at over 25,000 miles per hour, it would escape Earth's gravity entirely. It would fly out into space and never return. Scientists call that escape velocity. Stars work the same way. Every solar system has its own escape velocity. Any object moving faster than that limit flies free. And this comet was moving fast enough to escape not just any single star's gravity, but to cross the vast, empty space between star systems entirely. That journey is hard to picture. The distance from our Sun to the nearest neighboring star is about 25 trillion miles. If you drove a car at highway speed toward that star, you would still be driving more than 50 million years from now. The space between stars is almost nothing but emptiness. This comet crossed that emptiness. Moving at 152,000 miles per hour, it covered ground that no spacecraft humanity has ever built could match. Our fastest probe, Voyager 1, moves at about 38,000 miles per hour. This comet outpaced it by 4 times. Now, here is the part that changes everything. Because the comet entered our solar system on a hyperbolic path, it cannot stay. The sun's gravity grabbed it and bent its course. That bend is actually a curve in its trajectory, diverting it slightly as it swings around, but the comet is moving too fast for the sun to hold. After its closest approach to the sun, it will curve outward, back toward open space, accelerating again as it escapes, and it will never return. When local comets pass close to the sun, they loop back around eventually. Some take decades, some take thousands of years, but they come back. Their orbits are closed loops. This comet's orbit is an open line. It came in from the direction of the galactic center. It will exit toward a completely different region of space. At its current speed, it will pass the distance of Pluto's orbit within a few years. Within a few decades, it will cross the outer boundary of our sun's influence. Then it will keep going, for millions of years, in total silence, in total darkness, until some other star's gravity eventually catches it, or it wanders forever. Scientists have a name for the point of no return in orbital mechanics. Once an object crosses that threshold, no force available in nature can bring it back. This comet crossed that threshold the moment it entered our solar system. The window to study it was measured in months. Every day it traveled closer to the sun, scientists worked faster. Telescopes across the world coordinated their observations. Every measurement mattered. Every spectrum captured from its tail was a piece of data that would never be available again once it left. That urgency pushed research teams to work around the clock. They were racing against a clock set not in days but in orbital mechanics. And what they found as they studied this visitor's physical body shocked even the veterans who had spent decades watching space rocks. The size of this comet was something no one had predicted, 3.5 miles across. That is the estimated width of the solid icy core at the center of this comet. Scientists call that core the nucleus. And 3.5 miles is a number that sounds small until you put it next to something real. Mount Everest, the tallest mountain on Earth, rises about 5.5 miles above sea level. But measured from its actual base to its peak, the mountain spans roughly 12 miles of vertical rock. The nucleus of this comet, just the hard frozen core, measures 3.5 miles wide. It is a mountain-sized block of ice and rock that formed around a different star and has been traveling through the dark ever since. The Hubble Space Telescope made that measurement. To do it, Hubble analyzed how much light the comet reflected. A larger surface reflects more light. By comparing the comet's brightness against the amount of sunlight hitting it at that distance, scientists calculated the size of the solid core. 3.5 miles is significant for another reason. When a space rock of that size hits a planet, the consequences are catastrophic on a geological scale. The object that wiped out the dinosaurs 66 million years ago was estimated at around 6 miles wide. This comet's core is just under that size. Scientists confirmed early on that it posed zero threat to Earth, staying at least 150 million miles away at its closest point. But the size measurement gave everyone studying it a clear picture of what they were dealing with. A mountain-sized block of ancient frozen material, moving at 152,000 miles per hour, passing through our neighborhood. Beyond the core, the comet carries a much larger structure. As it approached the sun, solar heat began stripping away the outer layers of ice. Frozen gases, water, carbon compounds, and other chemicals vaporized and expanded outward. This expanding cloud of gas and dust surrounding the core is called a coma, and it stretched tens of thousands of miles wide. The entire visible structure, core plus coma, was enormous compared to the rocky core at its center. Behind the comet, the solar wind, a constant stream of charged particles blasting outward from the sun, pushed the released gas and dust into a tail. That tail extended for hundreds of thousands of miles behind the comet as it flew, longer than the distance from Earth to the Moon, pointing away from the sun like a banner, always pushed in the opposite direction of solar wind. The tail's structure told scientists a great deal about the comet's composition. Two separate tails formed. One was made of dust, curving gently behind the comet's path. The other was made of ionized gas, pointing almost perfectly straight away from the sun. Whenever scientists see that ion tail, they know the solar wind is actively stripping material from the comet's surface and pushing it outward at tremendous speed. All of this material, the coma, the dust tail, the ion tail, came from that original frozen core, a body that formed billions of years ago in a completely alien solar system. And now that it was warming up, it was beginning to reveal its secrets, including one that glowed bright green, 152,000 miles per hour. Read that number again. Now try to feel it. The fastest commercial airplane cruises at about 600 miles per hour. A bullet fired from a rifle travels roughly 2,000 miles per hour. Our fastest spacecraft, Voyager 1, moves at about 38,000 miles per hour, and it took 46 years to reach the edge of our solar system. This comet moves at 152,000 miles per hour. That is 4 times faster than Voyager 1. To feel that speed in a concrete way, picture the distance across the United States from New York to Los Angeles. That is roughly 2,800 miles. At 152,000 miles per hour, this comet would cross that entire distance in just over 1 minute, coast to coast in 60 seconds. Now picture the distance from Earth to the Moon, about 240,000 miles. The comet would cover that distance in roughly 90 minutes, faster than a long movie. That speed is what made this comet an interstellar traveler, rather than a trapped local object. Objects moving at typical solar system speeds get caught by the sun's gravity and settle into orbits. This comet was moving so fast when it entered that the sun could only bend its path slightly, like a bullet grazing the edge of a gravitational field. The speed also came with a hidden story. Interstellar objects do not start their journeys moving this fast. Comets in their home solar systems move at more modest speeds, pulled along by their own star's gravity. To reach 152,000 miles per hour, something violent had to happen. The leading explanation involves a gas giant planet. Giant planets like Jupiter carry enormous gravitational fields. When a comet or smaller body passes too close to a gas giant, the planet can fling it outward at tremendous speed, like a slingshot. If that ejected object was pointed in the right direction and the timing was right, it could escape its home star system entirely, carrying that extra speed with it forever. So the comet's extreme velocity is a scar, a record of a violent gravitational encounter that happened billions of years ago, in a solar system humans have never seen. That velocity also shaped everything about how scientists could study it. The comet was simply passing through. Every hour, it moved deeper into and then back out of the inner solar system. Telescopes had to coordinate globally to make sure someone was always watching, rotating observations across time zones as Earth itself turned. There was one other consequence of the speed. When moving that fast, even subtle interactions with solar radiation and the solar wind produced measurable effects. Scientists could track tiny changes in the comet's acceleration as solar pressure pushed on its expanding coma. Those measurements revealed details about the coma's density and composition that direct observation alone could not capture. Speed was the comet's defining trait, its origin, its nature, its timer. And understanding that speed opened a question that scientists had been quietly wrestling with since the first interstellar visitor appeared years earlier. Were these objects rare, or had we just been too blind to see them? The first one showed up in 2017 and immediately started arguments that have never fully ended. Astronomers at the Pan-STARRS Observatory in Hawaii detected an object moving through the inner solar system on a hyperbolic path. They named it Oumuamua, a Hawaiian word meaning roughly a messenger from far away, arriving first. Scientists confirmed immediately that it came from outside our solar system, the first interstellar visitor ever detected. Then they looked closer, and the arguments began. Oumuamua was strange in ways that no one had expected. Its shape, inferred from the way its brightness fluctuated as it tumbled through space, suggested something extremely elongated. Some estimates put it at a ratio of 10 to 1, like a cigar or a flat pancake tumbling end over end. No known natural object in our solar system has that extreme a shape. Then came the bigger mystery. As Oumuamua moved away from the sun, it accelerated. Not in the way gravity predicts. It sped up slightly beyond what orbital mechanics alone could explain. Local comets accelerate this way when solar heat vaporizes their ices, and the released gas acts like a tiny rocket thruster. But no one detected any gas or dust cloud around Oumuamua. No tail, no coma, just an oddly shaped rock, speeding up for no clear reason. A prominent Harvard astronomer published a paper suggesting the extra acceleration could be explained if the object was thin and flat, like a solar sail, a structure that uses sunlight pressure for propulsion the way a ship uses wind. The implication, left deliberately open, was that someone might have built it. Most scientists rejected that idea strongly. They pointed out that exotic shapes and unexplained accelerations in interstellar space could have many natural explanations that simply do not apply to objects born in our solar system. Nature produces strange things at scales, and in conditions humans have never directly studied. The debate was never fully resolved. Oumuamua left the solar system without giving scientists enough data to close the case. Then, in 2019, Borisov arrived. An amateur astronomer in Crimea named Gennady Borisov spotted it before any automated system did. Unlike Oumuamua, Borisov looked like a fairly ordinary comet. It had a visible coma and a short tail. Scientists analyzed its chemistry and found water ice, carbon monoxide, and other familiar compounds. The conclusion was encouraging. Comets in other solar systems appear to carry the same basic building blocks found in our own. Borisov was easier to study because it behaved in expected ways, but it was also smaller and less active than this new visitor. The data it provided was limited. 3 interstellar objects in under a decade. That was the count before this third visitor arrived. Astronomers began revising their estimates of how many of these objects passed through our solar system at any given time. Earlier models had assumed such visitors were extremely rare. The new models suggested dozens of interstellar objects might be traveling through our solar system at this very moment, simply too faint or too fast for current telescopes to catch. That realization changed the stakes entirely, and this third visitor arrived larger, faster, and more chemically active than anything that came before it, which raised the first real question about what it was carrying inside. The answer was written in a color no scientist expected to see. The photographs arrived from observatories around the world, and they all showed the same thing: a vivid, unmistakable green glow surrounding the comet's core. That color is not decoration. Every color a comet emits is a chemical signature, a piece of information written in light. And green, in the context of a comet, tells a very specific story. The green glow comes from a molecule called diatomic carbon. 2 carbon atoms bonded together in the frozen outer reaches of space, far from any star. This molecule sits inert and dormant inside the comet's ice, locked in place for billions of years. As the comet approaches the sun and the temperature rises, those ices begin to vaporize. The diatomic carbon molecules escape into the expanding coma around the comet's core. Then the sun hits them with ultraviolet radiation. That radiation carries enough energy to break the bond between the 2 carbon atoms. The molecule splits apart. In that moment of breaking, the atoms release energy in the form of light. That light lands at a specific wavelength, and that wavelength is green. The process happens continuously. As the comet heats up, new molecules vaporize. The sun breaks them. They emit green light. The result is a glowing emerald halo that surrounds the comet's core and expands into the coma. From a telescope, it looks like a green bubble floating in the dark. But here is the detail that caught scientists' attention. The intensity of this comet's green glow was exceptional. The The sheer amount of diatomic carbon vaporizing and splitting off suggested the comet's nucleus was rich in carbon compounds at a level not commonly seen in comets born in our own solar system. Carbon is the backbone of chemistry. It binds with oxygen, hydrogen, nitrogen, and dozens of other elements to form the molecules that make up living things on Earth. A comet packed with carbon compounds is essentially carrying a chemical toolkit. When astronomers detect that level of carbon richness in an interstellar visitor, it raises a question that scientists handle carefully. Could the same process that seeded Earth with complex carbon molecules long ago happen across the galaxy, carried by objects like this one? The idea that comets brought the raw ingredients for life to Earth is called panspermia, and it has serious scientific support. Local comets have delivered water and carbon compounds to rocky planets throughout our solar system's history. An interstellar comet carrying the same material, passing through dozens of solar systems across billions of years, could theoretically spread those same ingredients across vast regions of the galaxy. Nobody is claiming this comet brought life. Scientists are careful about that claim, but the carbon signature made clear that the chemistry driving life on Earth is found in visitors from beyond our solar system. The green glow faded from public attention quickly once the comet moved deeper into the sun's glare. But before it disappeared from view, scientists caught something else in the spectral data, something that did not belong. A metallic signal from an element that almost never appears in comets. Nickel belongs in metal, in coins, in stainless steel, in the iron-nickel cores of rocky planets like Earth. Nickel does not belong floating in the tail of a comet. When astronomers ran spectroscopic analysis on this comet's tail, they were searching for the standard checklist: water vapor, carbon monoxide, carbon dioxide, dust particles, the usual collection of chemicals that a warming comet releases. They found all of those. Then they found something else: nickel. In gas form, free-floating metal atoms drifting in the comet's coma. To understand how strange this is, you need to know how spectrometers work. When a telescope captures light from a comet's tail, scientists can split that light into its component wavelengths. The same way a prism splits white light into a rainbow, each chemical element and molecule absorbs and emits light at specific wavelengths. Like a fingerprint, scientists read those fingerprints to identify what a comet carries. The nickel fingerprint was clear and undeniable, and it was strong, far stronger than the faint traces detected in two local solar system comets in a different study from 2021. Metal vaporizes at temperatures around 2,800 degrees Fahrenheit. A comet's surface, even when heated by the sun, does not reach temperatures anywhere near that. Sunlight warms the surface enough to vaporize water, ice, and carbon compounds at relatively low temperatures. Pure metal should not be vaporizing at all at those conditions. So, where was the nickel coming from? Several explanations were proposed. One possibility is that the nickel is not in pure metallic form, but rather bound inside an organic molecule that breaks apart more easily under solar radiation. Some complex carbon-based molecules can carry metal atoms within their structure, and if those molecules are abundant in the comet's ice, they could release nickel gas when the sun breaks them apart. Another possibility involves the comet's unusual origin. If this object formed around a star with different elemental abundances than our sun, the building blocks of that star system would carry different ratios of metals. A star richer in heavy metals would produce dust and ice with higher concentrations of elements, like nickel already baked in from the beginning. Scientists have found nickel in the gas phase inside the comas of a handful of comets in recent years, so the presence alone is no longer shocking. The concentration level in this one, however, remains higher than expected, even accounting for its larger size and activity. The nickel mystery has not been solved. Studies are ongoing, and a full analysis will take years as researchers work through the data collected during the comet's brief passage. But what makes that mystery even harder to solve is what happened to the scientists trying to observe this comet right at the most critical moment. Just as the comet reached its most active and revealing phase, the world lost sight of it completely. Before the green glow, before the nickel signals, before any telescope had ever seen it, this comet was just ice. Cold, dark, silent ice. To understand what that means, you have to think about how old this object actually is. The universe is roughly 13.8 billion years old. Our solar system formed about 4.5 billion years ago. Stars older than our Sun formed billions of years before that, and around those older stars, the same process that built our solar system built others. Comets form in the cold outer regions of solar systems. Far from their star, temperatures drop so low that gas molecules freeze solid. Water, carbon dioxide, carbon monoxide, methane, and dozens of other compounds all crystallize into ice. Dust, grains, and silicate particles bind together in that ice. Over millions of years, gentle collisions and gravitational attraction build these frozen clumps into larger and larger bodies. Eventually, a comet nucleus forms, a solid ball of ancient frozen chemistry. This comet formed in that outer cold region of some unknown star system. Then something threw it out. Once ejected, it entered the space between stars. In that environment, the temperature is so close to absolute zero that even the faint warmth of starlight cannot reach it meaningfully. Absolute zero is the point where all molecular motion stops. The space between stars sits just a few degrees above that. In those conditions, nothing changes, nothing melts, nothing reacts. The chemistry locked inside a comet at that temperature simply waits for millions of years, possibly for billions. The ice that makes up this comet's core formed before Earth existed. Some of the water molecules inside it froze when our solar system was still a cloud of gas and dust. The carbon compounds locked in that ice are the original chemistry of a star system humans have never observed. They sat unchanged, in darkness, for a span of time that makes all of recorded human history look like the blink of an eye. Then our sun came into view. As the comet crossed the outer boundary of our solar system, it was still barely warming. The sun is just another star from a distance of billions of miles. But as the comet moved inward, closer and closer, the solar energy hitting its surface began to increase. The outermost layers of ice absorbed that heat. Then the temperature crossed a critical threshold, and those layers began to vaporize. Scientists call that process sublimation, where a solid skips the liquid state and becomes a gas directly. One moment ice, the next moment a cloud of expanding molecules rushing outward from the nucleus, pulling dust and small particles with them. That cloud was the comet's coma coming to life for the first time in its history. The first time solar radiation had ever touched those molecules. Astronomers watching through their telescopes were essentially watching ancient frozen chemistry thaw out for the very first time. And somewhere inside that chemistry, carried across the galaxy over billions of years, were clues about a world that no probe had ever visited. But the comet had one more appointment before scientists could study it fully. It was about to pass a planet. October 2025. The comet was moving fast, getting closer to the sun and heating up with every passing day. At this point in its trajectory, it had already crossed the orbit of Jupiter, crossed the orbit of the asteroid belt, and was driving deep into the inner solar system. The inner solar system is the neighborhood. Mercury, Venus, Earth, Mars, all of the rocky planets, all crammed into a region roughly 3 times the distance from Earth to the Sun. Compared to the colossal space the comet had crossed just to reach our solar system, the inner solar system is tiny, like a backyard, and the comet was cutting straight through it. As scientists tracked its path with increasing precision, the calculations revealed something striking. The comet's trajectory would bring it within 0.4 astronomical units of Mars. An astronomical unit is the average distance from Earth to the Sun, roughly 93 million miles. 0.4 of that is about 37 million miles. 37 million miles sounds enormous in everyday terms. But in the scale of planetary science, that is a close encounter. Mars and Earth themselves get as close as 34 million miles during their nearest approach. This comet was passing Mars at roughly the same distance that Mars and Earth share their closest. Scientists around the world recognize the opportunity immediately. Mars is the most studied planet beyond Earth. Multiple spacecraft orbit it. Multiple rovers sit on its surface. Every one of those instruments could potentially be turned toward the comet as it passed. The Perseverance rover, operating in Jezero crater on the Martian surface, was in a prime position. Its cameras were designed to photograph the Martian sky and terrain. As the comet swept past, mission teams on Earth sent commands to tilt Perseverance's cameras upward and capture images of the glowing streak moving across the thin Martian atmosphere. The data from that observation was gold. Earth's own thick atmosphere filters and blurs incoming light from space. From the surface of Mars, with its much thinner atmosphere and lower humidity, the comet appeared sharper. Scientists could study the structure of its coma with less interference from the environment between the comet and the observer. The Mars orbiters, including spacecraft built by several national space agencies, also turned their instruments toward the comet. Spectrometers measured the chemical signature of the coma as the comet flew past. The combined data package from the Martian encounter gave scientists a dataset they could not have gathered from Earth alone. There was something else about the Martian encounter that struck the public. The idea that a visitor from another star system had come close enough to a planet with rovers on it, close enough that our own machines could watch it pass, felt significant in a way that was hard to put into words. A probe from Earth, sitting on the Martian surface, watching a comet from another star fly past. But the moment scientists were most eager for was still coming. The closest approach to the Sun, perihelion, when the comet would be at its hottest, its most active, and its most revealing. The problem was, by then, no one on Earth would be able to see it. The cameras on Perseverance are not built for astronomy. They are built for geology, for reading rock layers in a Martian crater, for scanning the dusty ground for chemical signatures that might hint at ancient water. But on this particular evening, mission teams on Earth pointed those cameras straight up. The images came back hours later due to the communication delay between Mars and Earth. Scientists and engineers gathered around screens at mission control and waited. What came back was a streak, a bright, faintly greenish smear crossing the dark Martian sky. The comet's coma, illuminated by the sun from the other side, glowed with the carbon signature that had been detected from Earth-based telescopes weeks earlier. From the Martian surface, without Earth's thick blanket of atmosphere absorbing and scattering light, the comet appeared cleaner, sharper edges on the coma, the tail extending visibly behind it, pushed sideways by the solar wind. The thin Martian atmosphere is only about 1% as thick as Earth's. That near vacuum makes Mars a terrible place for humans to live, but a surprisingly good place to observe space. No significant atmospheric distortion, no humidity, no clouds blocking the view on most days. The Mars orbiters captured a different angle. Satellites orbiting Mars at hundreds of miles altitude photographed the comet from above the Martian surface, while Perseverance photographed it from below. Scientists were able to combine both perspectives to reconstruct a three-dimensional picture of the comet's coma structure as it appeared during the encounter. The coma was massive, stretched across a volume far wider than the planet Mars itself. The cloud of gas and dust surrounding the solid nucleus extended for tens of thousands of miles in every direction. The solid core, at the center, 3.5 miles wide, was completely invisible against the scale of the cloud surrounding it. The spectrometers on the orbiting spacecraft provided the richest data. As the comet passed, those instruments captured the chemical breakdown of the coma in real time. The water vapor, the carbon compounds, the diatomic carbon producing the green glow, all of it was logged. Scientists could see the rate at which the comet was losing material per hour as it heated up. That outgassing rate was extraordinary. The comet was shedding hundreds of tons of material per second at its peak activity. Material that had been frozen and locked inside for billions of years was now flowing outward into space, dispersed by the solar wind and gone forever. Every ton of material the comet lost was ancient chemistry from another star system, evaporating into the void. The window to capture it was narrow. Astronomers tracking the observations from Earth felt two competing emotions: excitement at the data pouring in, and a rising awareness that time was running out. The comet was heading toward the sun. Within weeks, it would disappear into the solar glare from Earth's perspective. The telescopes would go blind, the observations would stop, and at the worst possible moment, something else happened too. The databases went quiet. Telescopes are built to look away from the sun. That is the first rule of ground-based astronomy. Pointing an optical telescope at the sun without the proper filters is the fastest way to permanently destroy its mirror, its sensors, and potentially the eye of any person careless enough to look through it directly. As September 2025 arrived, the comet's trajectory brought it steadily closer to the sun from Earth's perspective. Not physically closer in the way a collision would work. The comet was approaching perihelion, its closest point to the sun in space. But from where Earth stood in its own orbit, the angle between the comet and the sun in the sky was shrinking. Picture holding a flashlight in the middle of a dark room. A moth circles the flashlight, getting closer and closer. As you watch the moth, it eventually gets so close to the glare of the bulb that the light washes it out entirely. You cannot see the moth anymore. The moth is still there. The moth is fine. You just cannot see it through the blinding glow of the light behind it. That is exactly what happened to this comet. It moved into the sun's blinding halo from Earth's point of view. The angular separation between the comet and the sun, the gap in degrees of sky between them, dropped below a threshold that even the most powerful ground-based telescopes could work within safely. Solar glare is not subtle. The sun is roughly 400,000 times brighter than the full moon. Any telescope pointed within a few degrees of it picks up so much scattered light that faint objects nearby become completely invisible against the noise. The comet, despite its size and activity, was still an extremely faint object compared to the overwhelming brightness of the sun. Space-based telescopes face a different version of the same problem. Most orbiting observatories are designed with sun shields that physically block solar light to protect their instruments. Pointing them anywhere near the sun's direction risks damaging or saturating those instruments. A small number of specialized solar observatories, instruments designed specifically to study the sun, can sometimes detect bright comets in the solar vicinity using coronagraphs. A coronagraph is essentially an artificial disk that blocks the sun's disk itself, revealing the fainter corona around it. Occasionally, a bright enough comet passes through that field of view and gets captured by a solar observatory. Scientists attempted exactly this. Several solar monitoring satellites were tasked with watching for the comet as it approached perihelion. Some brief detections were made, but the data was limited. The instruments were not optimized for comet science. The images were low resolution. Much of the detail that spectroscopic analysis from a proper telescope would have provided was simply unavailable. For roughly 6 weeks, the world's most capable observatories had almost no useful data on this comet. It was in there, somewhere, swinging around the sun, but it was invisible. And right in the middle of that blackout, the public databases stopped updating. Science communication runs on routine. Observatories detect objects. Scientists record measurements. Data gets submitted to centralized international databases. Those databases update automatically. Journalists check them. Space enthusiasts check them. Anyone curious about what is moving through the solar system can log on and see the latest data within hours. That pipeline broke down in September 2025. A gap in federal government funding created a situation where several agencies that normally maintain and update public-facing space databases experienced delays in their operations. Staffing at data centers shrank temporarily. Scheduled data releases were postponed. Websites that usually refreshed daily went days, then a week, without new entries. The timing was catastrophic for public trust. The most watched object in the solar system was already invisible to ground-based telescopes because of solar glare. Simultaneously, the public databases that track near-Earth objects and interstellar visitors stopped updating. From the outside, the combination looked like a deliberate blackout. Social media filled the gap immediately. Posts spread claiming that NASA was hiding a threat. Speculation ranged from an imminent impact to government concealment of alien activity. The comet's green glow, already unusual and visually striking, became fuel for theories about bioluminescent life forms or artificial signals. The comet's speed and trajectory, discussed in early press releases, were taken out of context and reframed in posts suggesting the object was accelerating toward Earth. None of it was true. The comet was never a threat to Earth. Its closest approach would keep it at least 150 million miles away. Scientists knew this within days of its initial detection. The math was clear and independently verified by multiple institutions across multiple countries. But math posted quietly on an institutional website does not compete with a viral post claiming the government has gone silent about an incoming object. The funding gap lasted a matter of weeks. Staff returned, databases resumed updating, press releases were issued. Scientists gave interviews explaining the orbital mechanics, the solar glare, the routine nature of the database pause. The explanations were accurate, and for people already following the story through reliable sources, the explanation was satisfying and complete. For a large portion of the public that had already seen the panic posts, the official explanation arrived too late to fully override the narrative that had taken hold. The comet eventually emerged from the sun's glare in December 2025. Observatories around the world turned back toward it. Data began flowing again. Scientists resumed publishing findings. The Vera C. Rubin Observatory in Chile, one of the most powerful survey telescopes ever built, spotted it first as it came back into view. By that point, the comet had already completed its closest approach to the sun. It was heading outward. Its most active phase was behind it. But during those 6 weeks of silence, a much older debate had been reignited. A debate that started with the very first interstellar visitor. A debate that some scientists had hoped would stay quiet. Was this object natural at all? By the second week of September 2025, two facts were true simultaneously. The comet was invisible to telescopes because of solar glare. The databases that track it had stopped updating. Both had simple scientific and administrative explanations. Together, they looked like something else entirely. The internet does not wait for press conferences. Within days of the database slowdown becoming publicly noticeable, posts were spreading across every major social platform. The framing was consistent. Space agencies had gone quiet. The comet had disappeared. Something was being hidden. Screenshots of empty database pages circulated widely. Text overlaid on telescope images claimed that the object's trajectory had been secretly updated to show an Earth approach. None of those screenshots showed real data. Several were fabricated. Many more were simply misreadings of how orbital data is formatted. The comet's name added a layer of confusion. The designation 3I-ATLS meant nothing to most people. Some posts interpreted the I in the name as a reference to intelligence or to something artificial. Comments speculated that the name itself was a coded message from scientists forbidden from speaking directly. That particular theory spread faster than any of the real orbital mechanics ever had. Amateur astronomers tried to push back. Several with legitimate credentials posted detailed threads explaining the solar glare geometry, walking through the orbital math step by step, showing exactly why the comet was behind the sun from Earth's perspective and when it would emerge. Those posts reached their own audiences. They did not reach the much larger audiences already consuming the panic content. The psychology of information gaps is well studied. When something people are paying attention to suddenly goes silent, the human brain fills in the silence with the most emotionally compelling explanation available. In the context of a fast-moving interstellar object, the most compelling explanation was threat. The brain defaults to danger when it cannot verify safety. Space agencies recognize the problem. NASA's Planetary Defense Team issued statements. The European Space Agency published explainers. Individual astronomers gave interviews. The core message was always the same. The comet would miss Earth by 150 million miles. It posed zero threat. The silence was operational, not conspiratorial. The irony was visible to scientists who had spent years trying to raise public awareness about actual planetary defense work. The very systems that detected this comet, the automated telescopes, the global tracking networks, the coordinated observatories, worked exactly as intended. The comet was spotted early. Its trajectory was calculated accurately. The threat level was assessed correctly and immediately. The story of successful planetary defense was being overshadowed by a story about institutional failure to communicate. The panic faded as the comet re-emerged in December and data flowed freely again. But the episode left a lesson about how quickly public trust can fracture when official channels go quiet during a high-stakes event, even for completely ordinary reasons. What the public did not yet know, because scientists were still analyzing the data, was that the comet itself had given them a genuine mystery to chew on, a mystery that did not involve conspiracies, a mystery that went straight to the question of what this object actually was. Nobody planned to find an interstellar comet on July 1st, 2025. The system that found it was built to do something else entirely. Planetary defense is the branch of space science, focused on detecting objects that could hit Earth. The threat is real. In 2013, a meteor about 65 feet wide exploded over the Russian city of Chelyabinsk without any prior warning. The blast shattered windows across an area roughly 35 miles wide and sent over 1,000 people to the hospital. The object was so small that it had never been detected before impact. After that event, global investment in sky survey programs increased significantly. The Asteroid Terrestrial Impact Last Alert System, the same network that caught this interstellar comet, was funded and expanded specifically to find small, fast-moving objects that earlier telescopes could miss. The system works by photographing the same patch of sky multiple times over a short period. Software then compares those images automatically. A star stays in the same position between images. A moving object shifts. The software flags the shift, calculates the object's movement speed and direction, and raises an alert if the trajectory suggests it could pose a threat. The telescopes in this network operate around the clock. They do not sleep. They do not take weekends. Multiple stations on different continents ensure that the full sky can be covered even as Earth rotates. When one station loses a patch of sky to daylight, another station on the opposite side of the planet takes over. The system was designed to catch small, slow-moving local asteroids. Instead, on July 1st, it caught an object moving so fast that its behavior immediately flagged as anomalous. The automated software had no specific protocol for interstellar visitors. It simply noticed that the object moved in a way that did not match any known solar system body and raised an alert. That alert reached human astronomers. Within hours, the hyperbolic trajectory calculation was complete. Within 48 hours, multiple independent observatories had confirmed it. Within 72 hours, the international astronomical community had issued an official designation. From detection to classification, the entire process took 3 days. That speed is significant. For context, the object that created the Chicxulub crater 66 million years ago and ended the age of the dinosaurs was never detected in advance. The Chelyabinsk meteor in 2013 was never detected in advance. Modern sky survey networks represent a fundamentally different level of awareness compared to any previous point in human history. Catching a comet that entered from outside the solar system traveling at 152,000 miles per hour from an unexpected direction above the orbital plane, and flagging it within days of observable approach, is a demonstration of capability that would have been impossible a generation ago. The network built to protect Earth from rocks ended up introducing humanity to a visitor from the stars, and that visitor was about to reveal a detail buried in old data that made scientists rethink the entire timeline of this story. The official detection date is July 1st, 2025. That is when the alert system flagged the object, and human astronomers confirmed it as real. That is the date the world was told about it. But the comet was already in the data before that. When scientists confirmed the detection, one of the first procedures in any major astronomical discovery is a recovery search. Teams pull archived images from sky survey databases stretching back weeks, months, or sometimes years, and scan them for the newly discovered object. The goal is to extend the observational arc to gather more data points across a longer timeline, which makes trajectory calculations more precise. Within 48 hours of the July 1st detection, the recovery search found the comet in images from June 14th, 17 days earlier. There it was, a faint smudge moving across a single archived frame, too dim and too unexpected for any automated system to flag at that point. June 14th was a Sunday. The image was taken by a robotic sky survey in Chile, processed automatically, stored in a database, and never looked at by a human eye until scientists came searching. 17 days of a confirmed interstellar visitor, sitting in a public database, undetected. That discovery raised questions that reverberate beyond this single comet. The sky is large. The telescopes scanning it, as numerous and capable as they are, cover each patch of sky relatively infrequently. A faint object moving fast across a sparsely revisited patch of sky could be photographed once, stored in a data archive, and never picked up by automated detection software if its brightness falls below the system's alert threshold. How many objects like this one have passed through our solar system in the last decade? The honest answer, according to scientists who study interstellar object statistics, is that the number is almost certainly higher than the 3 that have been officially detected. The current generation of telescopes can only reliably detect objects above a certain size and brightness. Smaller interstellar bodies, less active comets, dark rocky visitors with no coma to illuminate them, would pass through entirely unseen. The Vera C. Rubin Observatory, which began full science operations in 2025, is expected to change this dramatically. With a mirror nearly 28 feet across and a camera that covers an enormous area of sky in a single exposure, it will photograph the entire visible sky every few nights. The depth and coverage of its surveys should reveal interstellar objects far smaller and fainter than anything detectable with previous instruments. Scientists estimate that Rubin could increase the rate of interstellar object discoveries by a factor of several times compared to previous survey capabilities. The number of detections per decade is expected to rise sharply. That matters because each new detection is another sample, another piece of chemistry from another star system, another data point in the growing picture of how common organic molecules, water, and complex carbon compounds are across the galaxy. The comet in June 14th's data had no idea it was hiding in an archive. It was just moving, and that motion was carrying it toward the most intense moment of its entire journey, the meeting with the sun. The calculation took hours. It started with a handful of data points, the comet's position at different moments in time, and ended with a conclusion that changed everything. Every object in space has a trajectory, a path it follows based on its speed, its direction, and every gravitational force acting on it. For objects born in our solar system, that trajectory curves and loops. The sun's gravity pulls them into continuous orbits. Even highly elongated comets that take thousands of years to complete one loop are still bound. They still come back. The first thing scientists do when a new object is detected is calculate its orbital elements. These are a set of numbers that describe the shape of an object's path through space. The most important of those numbers is eccentricity, the measurement of how elongated or open the orbit is. For this comet, the eccentricity came back well above 1. That number is a mathematical hard line. Below 1, the orbit is closed. The object belongs here. At exactly 1, the orbit is a parabola, the boundary case. Above 1, the orbit is a hyperbola. The object is a visitor, not a resident. The team running the calculation immediately ran it again with different starting assumptions to check for errors. They got the same result. Then they shared the data with independent teams at other institutions. Within 12 hours, 3 separate groups had calculated the same eccentricity independently using different software. All 3 agreed. The number was above 1. To make sure they understood the full trajectory, scientists ran the path both forward and backward in time. Forward, the calculation showed the comet approaching the Sun, curving around it, and shooting back outward on a completely different heading than it arrived on. Back toward interstellar space, never to return. That confirmed the exit trajectory clearly. Running backward was more complicated. The comet's path into the solar system could be traced to the general direction of the Sagittarius constellation. But beyond that, the calculation became uncertain fast. The galaxy is full of stars, and every star exerts a tiny gravitational tug on any object passing near it. Over millions or billions of years of travel, those tiny tugs add up. The cumulative effect of billions of small gravitational nudges makes it mathematically impossible to trace the comet's exact origin. Scientists described it as trying to trace a billiard ball's origin after it has bounced off hundreds of walls in a dark room. You can point in a general direction. You cannot identify the exact pocket it came from. What the backward calculation did confirm was that the comet had been traveling for an enormous amount of time. Its entry, velocity, and direction were consistent with an object that had spent millions to billions of years crossing the emptiness between stars. The frozen chemistry inside it had been locked in darkness for that entire span, and now it was heading toward the brightest thing in our solar system. The Sun was about to do something to this comet that nothing in its billions of years of travel had ever done before. It was going to heat it to its absolute limit. October 31st, 2025, Halloween. The date was a coincidence. Orbital mechanics follow no calendar, but the timing gave the event a quality that journalists and social media posts could not resist. On the night when people across the country carved jack-o'-lanterns and handed out candy, a frozen rock from another star system was making its closest pass around the Sun, heated to temperatures it had never experienced in billions of years of existence. Perihelion is the word astronomers use for that moment. It comes from Greek roots meaning around the Sun. Every object on an orbital path has a perihelion, the single point in its journey where it comes closest to the Sun. For planets, that point recurs every year. For long-period comets, it might happen once every several thousand years. For this comet, it would happen exactly once in the history of our solar system, and then never again. The comet's perihelion distance was 1.4 astronomical units from the Sun. That put it just outside the orbit of Mars, which sits about 1.5 astronomical units out on average. So the comet's closest point to the Sun was near Mars's orbital distance but slightly inside it. To picture that in real scale, the Sun sits at the center. Earth orbits about 93 million miles out. Mars orbits about 142 million miles out. The comet at perihelion was about 130 million miles from the Sun. At that distance, the Sun is not as scorching as it would be from Mercury's orbit, but the solar radiation hitting the comet was still enormously powerful compared to anything it had experienced in interstellar space. And the comet was already showing signs of intense activity long before it hit perihelion. The outgassing that produced the green coma had started weeks earlier. By the time Halloween arrived, the comet was shedding hundreds of tons of material per second. The perihelion date was calculated with precision weeks before the event. Scientists knew exactly when and where the comet would be. The problem was that by late October, it was still behind the Sun from Earth's perspective. The solar glare that had been blocking observations since September had not yet cleared. The most dramatic moment of this comet's entire journey through our solar system happened while Earth's telescopes were pointing in the wrong direction. Everything scientists know about perihelion came from before the blackout and after it. The data captured during the Martian encounter in the weeks leading up to perihelion. The measurements taken by solar monitoring satellites, limited as they were, and the observations made in December when the comet finally emerged from the sun's glare and came back into view from Earth. From those combined data sources, scientists reconstructed what happened during the peak heating period. The comet survived, its nucleus held together. Many comets break apart when they approach the sun too closely, fragmented by thermal stress and tidal forces. This one made it through intact. That survival said something important about the structure of its nucleus. A solid, well-consolidated core holds together better than a loosely packed rubble pile. The fact that this comet came out the other side in one piece suggested its nucleus was denser and more coherent than many local comets. But the survival also meant the comet had been through the worst the sun could throw at it, and it was still carrying its secrets. A comet far from the sun is quiet, cold, almost invisible. A frozen ball drifting in darkness, releasing almost nothing. Move that same comet toward the sun, and it transforms. The process starts slowly. At the distance of Jupiter's orbit, some of the most volatile ices, the compounds that freeze at the lowest temperatures, begin to sublimate. Carbon monoxide and carbon dioxide are the first to go. They turn from solid to gas at extremely low temperatures, so even the faint warmth at Jupiter's distance is enough to start the process. As the comet crosses the asteroid belt and moves inward toward Mars, water ice begins to sublimate. Water is the dominant component of most comet nuclei, and when it starts vaporizing, the comet's activity explodes. Water molecules carry dust and fine particles with them as they rush outward from the nucleus surface. That material forms the coma, the broad cloud around the core that can stretch tens of thousands of miles across. By the time the comet reaches Earth's orbital distance, the Sun is delivering roughly 4 times the solar energy it delivers at Jupiter's distance. Because energy from the Sun drops off with the square of the distance, closer means exponentially more heat. At perihelion, the heating peaks. Every square foot of the comet's sunward surface is absorbing solar radiation at maximum intensity. The surface temperature, which began the journey near absolute zero in deep space, climbs to somewhere between 200 and 500 degrees Fahrenheit, depending on how reflective the surface material is. Under that heat, the nucleus surface becomes intensely active. Ice vaporizes in jets. Pressure builds beneath the surface as heat penetrates deeper layers. Occasionally, a pocket of trapped gas reaches the breaking point and blasts outward in a sudden outburst, throwing a plume of material into the coma that can temporarily double the comet's brightness. Astronomers watching comets approach perihelion sometimes see these outbursts happen. The comet brightens unexpectedly for hours or days, then settles back. Each outburst represents a fresh layer of ancient chemistry being stripped away and released into space for the first and last time. All of this outgassing also produces a physical effect on the comet's trajectory. Every jet of gas escaping from the surface acts like a tiny rocket thruster. The jets are not uniformly distributed around the nucleus. They concentrate on the sunward side, and their direction depends on the comet's rotation. The cumulative effect of all those tiny jets is called non-gravitational force, and it produces a measurable deviation from the trajectory that gravity alone would predict. Scientists tracking this comet included non-gravitational forces in their orbital calculations. The measurements helped them model the jet activity on the nucleus surface and estimate how much material the comet was losing per day. The answer was startling. At peak activity near perihelion, the comet was losing mass at a rate that would have reduced a smaller comet to almost nothing over a single pass around the Sun. This comet was large enough to survive, but the loss was real and permanent. Ancient chemistry, billions of years old, evaporating into the solar wind, gone forever. And in that evaporating material, something was forming that stretched across hundreds of thousands of miles of space. The sun does not just shine, it blows. Every second, the sun blasts a stream of charged particles outward in every direction. Protons, electrons, and heavier ions travel at speeds between 200 and 500 miles per second, filling the entire solar system with a constant invisible wind. That solar wind hits everything it encounters, and when it hits a comet's expanding coma, it sculpts that coma into a tail. The physics is clean and visual. The coma expands outward from the comet's nucleus in every direction, but on the side facing away from the sun, the solar wind slams into the outflowing gas and pushes it. The charged gas molecules in the coma, which have been ionized by solar radiation, respond strongly to the electromagnetic forces in the solar wind. They get swept back into a long, narrow streamer pointed directly away from the sun. This is the ion tail. It always points straight away from the sun, regardless of which direction the comet is moving. A comet approaching the sun races toward it with its tail stretched out behind. A comet moving away from the sun travels with its tail still pointing away from the sun, meaning the tail actually goes out in front of the comet's direction of travel. The comet leads with its face and drags its tail behind only when approaching. It exits tail first. The dust tail is different. Dust particles are larger than ions and do not respond as strongly to electromagnetic forces. Instead, they feel the pressure of photons, actual particles of light pushing against them. Radiation pressure from sunlight pushes the dust back and slightly to the side, curving the dust tail gently behind the comet's orbital path. The result is two distinct tails extending from the comet's head in slightly different directions. One straight and narrow, pointing perfectly away from the sun. One broader and gently curved, trailing along the orbital path. During this comet's peak activity near perihelion, the ion tail stretched for an estimated several 100,000 miles. To picture that, the distance from Earth to the Moon is about 240,000 miles. This comet's ion tail extended longer than that distance, a glowing streamer of ancient gas from another star system, stretched across space by the force of our sun's wind. That tail was a direct interaction between two star systems. Gas that formed around an alien star, frozen for billions of years, now being pushed and shaped by the energy pouring from our star. Scientists studying the ion tail used its structure to gather information about the solar wind conditions at the comet's location. Kinks and variations in the ion tail revealed turbulence in the solar wind flow, caused by magnetic field structures inside the solar wind called current sheets. As the comet's tail crossed through those magnetic boundaries, the tail would suddenly disconnect and reform. Astronomers call this a disconnection event, and it happens when the magnetic polarity of the solar wind reverses. Every structure in that tail held information about the sun, about the comet, about the chemistry being released, and about something that the tail's composition was quietly raising. A question about where this comet truly came from. The paper appeared in September 2025, right in the middle of the tracking blackout. The timing was not planned, but the impact was immediate. A prominent Harvard astrophysicist published a preprint, a paper released publicly before going through the full peer review process. The paper argued that several characteristics of this comet, taken together, warranted serious consideration of an alternative explanation. The alternative was that the object was artificial, a probe, sent deliberately. The argument rested on three pillars. The first was speed. At 152,000 miles per hour, this comet moved faster than most natural interstellar objects would be expected to travel given typical stellar ejection mechanisms. The paper noted that while high-speed ejection by a gas giant was plausible, the extreme velocity remained statistically unusual. The second was the trajectory. The comet's path through the solar system was a clean hyperbola, a strikingly precise curve that, in the paper's framing, showed unusually little deviation from a theoretically perfect trajectory for a passive object. The author suggested this warranted examination. The third was the chemical composition. The elevated nickel signatures and the unusual carbon richness, the paper argued, were outliers from what would be expected based on known interstellar medium chemistry. The Harvard astronomer had made similar arguments about Oumuamua years earlier. That earlier proposal sparked intense international debate that never reached a scientific consensus. This paper attempted to apply the same framework to a different object and asked whether the pattern of unusual properties in interstellar visitors deserved systematic investigation. The response from the broader scientific community was swift and pointed. Multiple teams published formal rebuttals within weeks. They argued that each of the three cited characteristics had clear natural explanations. The speed was high, but within the range produced by close gravitational encounters with large planets. The trajectory appeared clean, because a clean hyperbola is exactly what any unaccelerated interstellar object would produce. And the chemical signatures, while unusual for solar system comets, fell within the range of what was plausible for an object formed around a chemically different star. The most direct rebuttal pointed to the comet's coma and tail. An artificial probe would carry no ice. Sublimating ice is the engine behind every behavior scientists observed. The green glow, the ion tail, the outgassing jets, the measured mass loss per second. A metal probe, however advanced, does not grow a coma tens of thousands of miles wide when it gets close to a star. The scientific community's position was clear. The comet was natural. The behaviors matched. The proposal was extraordinary, without being supported by extraordinary evidence. But the debate had escaped the journals. Online, the Harvard paper was treated as confirmation of what many had already suspected during the database blackout. The scientific rebuttals received less attention. The actual mystery about this comet was never about whether it was built. The actual mystery was where it came from, and that question had no answer. The comet gave itself away, not through a press release, through ice. When scientists want to determine whether a distant object is natural or artificial, the most reliable evidence comes from behavior, specifically the behavior that only frozen chemistry can produce. From the moment this comet entered the inner solar system, it behaved exactly like an active comet. A coma formed and expanded outward from the nucleus. The coma stretched tens of thousands of miles in every direction. That coma glowed green because diatomic carbon molecules were vaporizing and being broken apart by ultraviolet radiation. A tail formed. Then a second tail formed. Both grew longer as the comet approached the sun. No known artificial structure produces this behavior. The green emission from diatomic carbon requires actual carbon-bearing ice sublimating under solar heat. The dust tail requires actual dust particles being carried off the surface by vaporizing gas. The ion tail requires actual ionized molecules being swept back by the solar wind. Every single observable feature of this comet's appearance pointed to one thing: sublimating ice in a nucleus. NASA planetary scientists also pointed to the measured rate of non-gravitational acceleration. The jets vaporizing off the comet's surface were measurable. Scientists tracked small deviations in the comet's trajectory caused by those jets. The pattern of those deviations was consistent with a rotating nucleus with active venting regions, exactly what a natural comet produces. An artificial probe, if it were being propelled by some kind of thruster, would produce a very different acceleration profile, steady or controlled, rather than the uneven, thermally driven pattern observed. The comet's rotation also supported the natural interpretation. The nucleus rotated as it moved, tumbling slightly as it went. Active venting regions came into and out of sunlight as the nucleus turned. Scientists detected brightness variations in the coma that corresponded to this rotation, a natural tumbling frozen body, behaving like one. The Hubble Space Telescope's measurements of the nucleus size were also consistent with a natural comet. At 3.5 miles across, the nucleus was well within the size range of large comets observed in our own solar system. Artificial structures of that size, built from materials capable of surviving billions of years of interstellar travel, remain completely outside the range of anything humans have ever built or theorized building. The scientific community's rejection of the artificial hypothesis was based on evidence, not on reluctance to consider the idea. The idea was considered. The data spoke against it at every point. What the data did support was something almost as extraordinary. A comet carrying chemistry from a completely alien star system, formed in conditions humans have never directly observed, reaching our neighborhood after billions of years of travel, and spending a brief few months giving every available telescope a look at what other solar systems are made of. That is the actual story. And it raised questions about the comet's home that may never be answered. Scientists would love to know exactly which star system this comet came from. The answer would tell them about the conditions in that system, the chemistry, the age, whether rocky planets orbited there, whether the ingredients for life were present. That answer is almost certainly out of reach. To trace the comet's origin, scientists run the trajectory backward in time. They take the comet's current position, speed, and direction, and reverse the math to walk its path back through the galaxy. In principle, this should lead to a source. In practice, the galaxy makes it nearly impossible. The problem is gravity. Not from one star or two stars, from hundreds of billions of stars. Every star in the galaxy exerts a gravitational force on everything around it. For most purposes, stars that are far away exert forces too small to matter on a single calculation. But over millions or billions of years of travel, the comet passed within meaningful gravitational range of many stars. Each close pass bent its trajectory slightly, each bend compounded on the ones before it. The path the comet took through the galaxy was not a straight line. It was a slow, subtle curve shaped by countless gravitational interactions. Running the math backward means accounting for every one of those interactions in reverse. But scientists do not know exactly where every star in the galaxy was millions of years ago. Stars move, the galaxy rotates. Our own sun orbits the galactic center roughly once every 225 million years. Every other star does too, at its own speed and orbital path. The uncertainty compounds fast. Even with the most powerful supercomputers available and the most detailed maps of stellar positions and velocities, tracing this comet's path back further than a few million years produces results with enormous error bars. The cone of possible origin points grows so wide that it spans large sections of the galaxy. Scientists did manage to trace the path back to the general direction of the constellation Sagittarius. That direction points toward the inner galaxy, toward the denser central regions where stars are more tightly packed. If the comet originated from that general region, it formed in an environment where star systems are closer together and gravitational encounters between passing objects are more frequent. But a general direction is not a star. There are hundreds of millions of stars in that direction. Any one of them, or none of them, could be the comet's birthplace. One additional challenge is the age of the comet itself. If it formed 4 billion years ago, the star it formed around may no longer exist. Stars die. Medium-sized stars like our Sun eventually expand into red giants and shed their outer layers. Larger stars explode as supernovae. If the comet's home star is gone, there is no object to trace back to. The comet carries the only record of its origin inside its frozen chemistry, and scientists spent the entire brief window of its passage trying to read that record before it disappeared back into the dark. What they read was surprising. Getting thrown out of a solar system takes violence. Comets do not wander out voluntarily. They form in the cold outer regions of their star's influence, gravitationally bound, moving in slow orbits far from their sun. Without something dramatic happening, they stay there for the entire lifetime of their star, billions of years, orbiting in cold darkness, going nowhere. For this comet to have crossed interstellar space at 152,000 miles per hour, something had to launch it, and the most likely culprit was a gas giant planet. Gas giants are the heavyweights of solar systems. Jupiter, in our own system, is so massive that its gravitational field reaches deep into the outer solar system and regularly redirects smaller objects. Comets and asteroids that pass too close to Jupiter get their orbits bent sharply. Some get flung inward toward the Sun. Some get flung outward toward the edges of the solar system. When an object gets flung outward at high enough speed, it can escape its star's gravity entirely. This is called gravitational scattering. The gas giant essentially uses its own orbital energy to throw the smaller object outward. The planet loses a tiny, imperceptible amount of its orbital energy in the process. The comet gains enough speed to break free. For this comet, the encounter that launched it was likely a close pass with a gas giant planet orbiting its home star. If the comet's original orbit brought it near the giant planet at the right angle, the planet's gravity could have swung the comet around and added enough speed to push it past escape velocity for that star system. The angle and timing of such an encounter must be precise. Most comets scattered by gas giants do not reach escape velocity. They just end up in new, more elongated orbits. Only a fraction of scattering events produce true ejections. But gas giants in solar systems scatter millions of comets over billions of years. The fraction that escape is small, but the number of total ejections across the galaxy over time is enormous. Scientists estimate that the galaxy contains trillions of interstellar objects right now, wandering between stars, the cast-offs of billions of solar systems scattered over billions of years. The vast majority will never interact with any star again. They will travel in darkness forever. A tiny fraction will pass close enough to another star to be deflected into that star's inner system, giving that star's planets a brief visit. Earth got such a visit in July 2025. The violent launch from a gas giant also explains the comet's extreme speed. A gentle gravitational tug at the edge of a solar system produces a slow ejection. A close, high-energy encounter with a massive gas giant can produce speeds well above the typical escape threshold. That extra speed carries the comet across the interstellar void faster and farther than a slower ejection would. Whatever gas giant launched this comet, it sent a piece of its solar system's history directly into ours, and the chemistry it carried raised a deeper question about the star it came from. Chemistry is a fingerprint. Every star in the galaxy has a slightly different mix of elements based on when and where it formed. And the comets that form in a star's outer regions carry that same chemical signature, frozen in their ice for billions of years. Our Sun formed about 4.5 billion years ago from a cloud of gas and dust enriched by previous generations of stars that had lived and died before it. The elements in our solar system, the ratios of carbon to oxygen to nitrogen to silicon, reflect the specific cloud our Sun was born from. A star born in a different region of the galaxy, or at a different time, formed from a differently enriched cloud. The ratios are different. The proportions of heavy metals, complex carbon compounds, and volatile ices would all vary. The chemical analysis of this comet's coma pointed to an origin environment with different proportions than what our solar system's comets carry. The most notable signals were the elevated nickel content and the unusually high carbon richness relative to oxygen. In the comets of our own solar system, carbon and oxygen appear in more balanced proportions. The strong carbon excess in this visitor's coma suggested it formed around a star whose protoplanetary disk, the cloud of gas and dust that collapsed to form planets and comets, was carbon-heavy by comparison. Carbon-rich stellar environments exist. Stars in certain regions of the galaxy, particularly older stars formed when the galactic chemical mix was different, can produce solar systems with more carbon relative to oxygen than what we see locally. In those systems, instead of silicate rock minerals like those making up Earth's crust, planets and comets form with more graphite, carbide minerals, and exotic carbon compounds. A comet from such a system would carry that chemistry frozen inside it. When it warmed up near our Sun, it would release those compounds at higher concentrations than a local comet would. This interpretation is not certain. Scientists are careful to note that the sample size of interstellar objects is 3. Drawing firm conclusions about stellar chemistry from the coma of a single passing comet requires caution. The unusual readings could have other explanations, including the comet's age, its specific formation history, or chemical processing it underwent during its billions of years of travel through the interstellar medium. Cosmic rays, the high-energy particles that fill the space between stars, can alter the surface chemistry of interstellar objects over long time periods. Some of what the comet released when it warmed up may have been processed by cosmic ray bombardment during its journey, rather than representing purely original star system chemistry. Separating original chemistry from travel process chemistry is one of the key analytical challenges in interpreting interstellar comet data. Scientists are working through those questions with the data collected during the comet's passage. The tentative picture that emerged was of a comet that formed in a richer, heavier environment than our own solar neighborhood, older, more carbon-dense, a different world entirely. And that difference had implications far beyond this single object. 3 confirmed visitors in under a decade, that number carries more weight than it might seem. For most of human history, scientists assumed the solar system was an island, separated from every other star system by distances so vast that material exchange between them was essentially zero. The chemistry of our solar system was our chemistry. The chemistry of other solar systems was theirs. The two did not mix. The detection of Oumuamua in 2017 cracked that assumption. The detection of Borisov in 2019 reinforced it. The arrival of this third visitor, larger and more chemically active than either of the first two, confirmed it more powerfully than ever. Solar systems are not isolated. They leak. Every solar system with gas giant planets is constantly throwing material outward. Comets get gravitationally scattered. Asteroids get ejected. The smaller rocky debris of planetary formation gets sent tumbling into interstellar space over billions of years of gravitational interactions. Some fraction of that material, moving fast enough, escapes its home star and joins the galaxy's vast population of interstellar wanderers. Those wanderers travel for millions of years. Most never encounter another star closely enough to enter its inner system, but some do. Our solar system has been receiving these visitors since it formed. We just had no way to detect them until recently. The current estimate, based on statistical modeling of how frequently such objects pass through, given the rates at which we are detecting them now, suggests that thousands of interstellar objects pass through the solar system every year. The overwhelming majority are too small, too dark, or too fast to detect with current equipment. Only the largest and most active ones, the ones that develop bright comas as they approach the sun, become visible. Each detected visitor is a sample from another solar system. Its chemistry represents conditions from a place humans have never directly observed. The water in its ice may have formed around a star that died billions of years ago. The carbon in its coma may have crystallized in a disk of material circling a star in the galactic center. If the galaxy is continuously exchanging material between solar systems at this rate, then the building blocks of life are not unique to Earth's neighborhood. They are common, distributed, moving. Every solar system is seeded, over time, with chemistry from every other solar system within gravitational reach. That picture changes the framework for asking where life can exist. If the basic carbon and water chemistry of life reaches new planetary systems via interstellar objects, then life does not need to reinvent its chemistry from scratch each time. The ingredients arrive pre-assembled, carried across the galaxy in frozen packages ejected by distant planets billions of years ago. The comet that arrived in 2025 was a 3.5-mile piece of that process. One data point in an ancient, ongoing exchange that has been happening since the first stars formed, and a telescope was about to finally see it again. December 2025. The comet had been invisible for nearly 3 months. The last reliable data came from before the solar glare swallowed it in late September. The Mars Encounter observations had been processed and published. The early spectroscopic data had been analyzed. Scientists knew what they had captured, but since October, the most dynamic phase of the comet's journey, the perihelion passage, had happened entirely out of sight. Then, in the first week of December, The Vera C. Rubin Observatory in the Atacama Desert of northern Chile turned its enormous mirror toward the patch of sky where orbital calculations predicted the comet should be emerging. The Rubin Observatory is built differently from the telescopes that first detected this comet. Its primary mirror is nearly 28 feet across. Its camera, the largest digital camera ever built for astronomy, covers an area of sky roughly the size of 40 full moons in a single exposure. Its design purpose is survey speed, rather than staring at one small patch of sky for a long time. It photographs enormous areas of sky repeatedly, building up a complete picture of the southern sky every few nights. The comet showed up in the first scan, fainter than it had been at its peak near perihelion. The coma had shrunk as the comet moved away from the sun and the heating dropped off. The tail was shorter, but the comet was there, clearly visible, moving outward on its exit trajectory at high speed. Scientists who had been waiting for the re-emergence described the detection as a relief. The models had predicted where the comet should be based on the pre-blackout trajectory data. The fact that the Rubin Observatory found it exactly where the models predicted was a confirmation that the orbital calculations had been accurate throughout. The comet had gone behind the sun, survived perihelion, and come out the other side on the expected path. The re-emergence gave scientists a second observational window, a brief one, because the comet was now accelerating outward and fading fast, but enough to gather post-perihelion data that could be compared against the pre-perihelion observations. That comparison was valuable. Scientists wanted to know how much the comet had changed during its closest approach to the sun. Had the nucleus lost significant mass? Had any surface features changed? Was the composition of the outgassing different after perihelion than before? The post-perihelion data showed the comet had lost a meaningful fraction of its surface material. The total coma activity was lower than at peak, consistent with less volatile material remaining exposed on the nucleus surface after the intense heating period. The nucleus appeared intact. No fragmentation had occurred. The green carbon glow was still present but weaker. The nickel signatures were fainter. The comet was cooling down and going quiet as it moved outward. Quieter, but not done, because the question of what scientists had actually learned from this entire passage was only beginning to be answered. The question came up within hours of the July 1st detection. Would this comet hit Earth? It is the first question anyone asks. It was the first question the planetary defense teams answered, and they answered it definitively within days of the detection, long before most of the world had even heard the comet's name. The math that confirms safety is the same math that describes the comet's trajectory. When scientists calculate orbital elements and get an eccentricity well above 1, they simultaneously calculate every point along that hyperbolic path, the position at every date, the closest approach to each planet, the minimum distance to Earth. For this comet, the minimum Earth approach distance came out at approximately 150 million miles. That is roughly 1.6 times the distance from Earth to the Sun. In solar system terms, 1.5 times the Earth-Sun distance is enormous. In everyday terms, 150 million miles is a gap so vast that even the comet's exceptional speed would take it over 1,000 hours to cross. To generate a threat, a comet needs to cross Earth's orbit at the same moment Earth is at that crossing point. Missing Earth's position in its orbit by even a few weeks means a miss of tens of millions of miles. This comet's path crossed the plane of the solar system at a point far from Earth's location at any point in its passage. The calculation was independently verified by multiple teams. In the same way, the initial hyperbolic trajectory confirmation was run by separate groups with separate software. The European Space Agency's Planetary Defense Coordination Office confirmed it. The International Astronomical Union's Minor Planet Center confirmed it. University research groups in Japan, Germany, and the United States confirmed it. Every single calculation agreed. Zero threat. The reason those independent confirmations matter is not because any single team's math was uncertain. They matter because public trust in high-stakes astronomical claims requires transparent, redundant verification. When multiple institutions in multiple countries using different methods reach the same conclusion, the result is about as certain as science gets. Scientists made all of this data public within days of the initial detection. The orbital elements, the trajectory plots, the closest approach distances. All of it was uploaded to public databases and explained in plain language press releases. The irony of the panic that followed weeks later, during the database blackout, was that the safety confirmation had been published long before the silence began. The information was available and accurate from the start. What the safety confirmation also did was free scientists to focus entirely on the science. With no emergency response protocols activated and no threat assessment consuming resources, every telescope, every team, and every instrument could focus purely on understanding this visitor while it was still visible. That science was now producing results that reached far beyond this single comet. Every substance the comet released near the Sun was a message from another world. When the spectroscopic data came in from observatories around the globe, scientists were not just cataloging chemicals. They were reading the composition of a solar system that no probe had ever visited, a system whose star might be gone, a system located somewhere in the direction of the galactic center, possibly billions of light-years away, possibly only a few hundred light-years. The water vapor in the comet's coma was the first major finding. Water is the baseline. The fact that an object from outside our solar system carried substantial water ice confirmed what the Borisov observation had suggested years earlier. Water is common in the universe. It forms wherever oxygen and hydrogen meet in cold environments, and oxygen and hydrogen are two of the most abundant elements in the galaxy. The presence of water ice in this comet strongly suggests that other solar systems produce water-bearing bodies in their cold outer regions, just as ours did. The carbon compounds were richer and more complex. The diatomic carbon producing the green glow was expected, but spectroscopic analysis also detected signatures consistent with more complex organic molecules, chains of carbon and hydrogen atoms that form the structural backbone of life's chemistry. These molecules, called hydrocarbons, appear in meteorites that fall to Earth from our own solar system's history. Finding them in material from outside the solar system extended their distribution across a second data point. 2 data points are not a pattern. Scientists are careful about that, but they are more than one, and that matters in astronomy. The silicate dust in the comet's tail was also measured. Silicates are the minerals that make up rocky planets. The specific types of silicate dust and their proportions tell scientists about the temperature conditions in the region of space where the comet formed. Silicate crystallization requires specific temperature ranges. Reading the dust composition gives a snapshot of the thermal environment in the outer disk of the comet's home star. The combined picture from water, organics, silicates, carbon compounds, and metallic traces was a rough chemical portrait of an alien solar system, imprecise, limited by observation, time, and distance, but real. For scientists searching for life elsewhere in the universe, each of these measurements adds to a fundamental argument. The chemistry of life is not exotic. It appears in interstellar visitors. It appears in local comets. It appears in meteorites. It appears in interstellar molecular clouds detected across the galaxy. Life's raw materials are common, distributed, and ancient. The question of where life exists is increasingly a question of where those materials found the right conditions to assemble into something more. And understanding those conditions starts with understanding the solar systems that produce the chemistry we are finding. The comet did not come from inside the solar system. Nothing in the planetary defense network had ever been designed specifically to catch something originating outside it. The automated telescopes sweep the sky for rocks moving in predictable local patterns. An object diving in from above the orbital plane at 152,000 miles per hour was never in the original threat matrix, and yet the system caught it. That is the most important operational fact about this entire event. The planetary defense infrastructure, built over the last 2 decades specifically to prevent an extinction-level or civilization-threatening impact, detected an interstellar object crossing from a completely unexpected direction within days of it becoming detectable. The Chelyabinsk meteor in 2013 was a reminder of what happens without adequate warning. 65 feet wide, no detection, blast equivalent to roughly 30 times the Hiroshima atomic bomb. Windows shattered across a wide area, over 1,000 injuries. An object of that size arrives with essentially no warning under the survey capabilities that existed then. The 2025 detection demonstrated how much the situation has changed. An object millions of times larger, arriving from outside the solar system on a trajectory no planetary defense model had specifically anticipated, was caught early and tracked precisely. The trajectory was confirmed accurate. The threat level was assessed correctly. The observations were shared globally. The only piece that did not work smoothly was the communication side, the database slowdown, and the public panic that followed. The detection, tracking, and threat assessment worked exactly as designed. The lesson the planetary defense community took from this event was about redundancy and communication. Technically, the systems performed. Publicly, the gap between accurate scientific information and public perception became a problem almost immediately when official channels went quiet. The recommended response, adopted by several space agencies in the months following the event, involved establishing automated, publicly visible threat confirmation systems that update continuously and cannot be interrupted by administrative funding gaps. If the orbital mechanics say 0 threat, that number should be visible and updating in real time, independent of government staffing levels. The comet itself was never a threat, but the event exposed a gap between scientific readiness and public communication that, in a scenario involving an actual threat, could produce serious consequences. The comet passed safely, the systems improved, and the object that triggered all of it was now heading for the outer edge of the solar system, picking up speed. The exit began the moment the comet reached perihelion. From October 31st onward, the comet was moving away from the Sun. The same orbital mechanics that pulled it inward now worked in reverse. The Sun's gravity slowed the comet slightly as it climbed away from the Sun, the way a ball thrown upward slows as gravity pulls at it. But the comet was moving far too fast for the Sun to stop it. The gravity slowed it briefly. The comet kept going. By December, the comet had crossed back out past the orbit of Mars, still moving, still visible to the most powerful telescopes, though fading fast as the distance grew and the solar heating dropped off. The green coma was dimming. The tail was shrinking. The comet was going cold again. Early in 2026, the comet crossed the asteroid belt heading outward. The belt is not a wall. It is a wide region populated sparsely enough that objects cross it routinely without hitting anything. This comet had already crossed it inbound without incident. It crossed outbound the same way. By mid-2026, the comet was approaching the orbit of Jupiter. At that distance, water ice stopped sublimating as effectively. The coma activity fell off dramatically. The comet was essentially going dormant again, refreezing as the Sun's energy dropped with distance. Beyond Jupiter's orbit lies the realm of Saturn, Uranus, and Neptune. Crossing those distances takes years, even at the comet's extraordinary speed. By the end of the decade, the comet will be somewhere in the outer solar system, far beyond Neptune, still moving outward and accelerating very slightly as the Sun's gravity weakens its hold. By the 2040s, the comet will approach the heliopause, the boundary where the Sun's influence gives way to interstellar space. The solar wind drops off. The magnetic bubble the Sun creates around the solar system gives way to the interstellar medium. Voyager 1 crossed this boundary in 2012 after 45 years of travel. This comet, moving 4 times faster, will cross it far sooner. Once beyond the heliopause, the comet re-enters the environment it spent billions of years traveling through. the near-zero temperature of interstellar space. The constant low-level bombardment of cosmic rays, the faint gravitational tugs of distant stars pulling on it from every direction. Any remaining active surface will refreeze completely. The last traces of the coma will thin out and disperse. The comet will become a dark, silent, frozen object again, indistinguishable from the billions of other interstellar wanderers. It will join in the darkness between stars, and it will keep moving. 152,000 miles per hour, pointed away from our solar system forever. There will be no second pass, no return orbit, no future visit. Humanity had one chance. When Halley's Comet passed Earth in 1986, it disappointed many observers. Too faint, too distant. The conditions were poor, but no one who missed it felt the loss too deeply. Halley's Comet returns every 75 to 79 years. The people alive in 2061 will get another chance. Their children will see it again after that. This comet offers no such consolation. The hyperbolic orbit is a mathematical statement of permanence. Once an object is on a hyperbolic trajectory, there is no return. The orbit does not curve back around. It opens outward and continues forever. When this comet crossed the outer boundary of our solar system, it was already gone in the only sense that matters for scientific observation. That finality shaped every decision scientists made during the window when the comet was visible. It explained the urgency. It explained why teams worked through the night. It explained why observatories on multiple continents coordinated their schedules to ensure continuous coverage. Every hour the comet spent inside the detectable range was irreplaceable. Scientists discussed proposals for a rapid response mission that could fly a spacecraft to intercept the comet during its passage. The idea was technically feasible in concept. A fast spacecraft launched toward the comet's projected path could potentially match trajectories long enough to take close-up images, sample the coma, or even land on the nucleus. The problem was time. The window between detection and perihelion was roughly 4 months. Designing, building, testing, and launching a spacecraft to an interstellar comet in 4 months is beyond current capability by a wide margin. The fastest spacecraft humanity has ever launched took years of preparation. The scientific community responded to this limitation by recommending investment in pre-built, ready-to-launch spacecraft that could be deployed rapidly when the next interstellar object is detected. The concept, sometimes called an interstellar object rapid response mission, would involve keeping a small spacecraft in a ready-to-launch state, requiring only a few weeks of final preparation before dispatch. Given that the Vera C, Rubin Observatory, and next-generation sky surveys are expected to detect interstellar objects earlier in their approach, the window for response is likely to be longer for future visitors. A visitor detected 2 years out rather than 4 months out would allow genuine mission planning time. The data gathered remotely from this comet, from Earth-based telescopes, from the Hubble Space Telescope, from the Mars orbiters and rovers, from solar monitoring satellites, was extraordinary by any historical comparison. Scientists collected more data on this interstellar visitor than on the first 2 combined. But everyone who worked on the analysis knew what they had not gotten: close-up images of the nucleus, direct chemical sampling of the coma, a look at what the surface actually looks like up close. The comet is gone, the data is permanent, and the next visitor is already out there somewhere. 3 visitors in less than 10 years, the first in 2017, the second in 2019, the third in 2025. That rate is not noise, it is a signal. Before Oumuamua, the theoretical models that predicted how often interstellar objects pass through our solar system were based on educated estimates with no observational grounding. The estimates varied widely. Some models suggested a visitor, detectable by current telescopes, might show up once every decade. Others said once a century. 3 detections in under a decade pushed those models toward the higher end. And here is the critical detail. All 3 detections were made with telescopes that were never designed to find interstellar objects. The Asteroid Terrestrial Impact Last Alert System found this latest one while scanning for local threats. Pan-STARRS found Oumuamua while doing a general sky survey. Borisov was found by an amateur astronomer with a private telescope. The detection rate with purpose-built, optimized equipment is expected to be dramatically higher. The Vera C. Rubin Observatory changed the calculation. With its ability to photograph the entire southern sky every few nights to extraordinary depth, it is expected to detect interstellar objects that earlier surveys would have missed entirely. Objects too faint, objects too far out, objects approaching from directions and at angles that older surveys sampled too infrequently. Astronomers working on interstellar object statistics now estimate that there are likely over 1 trillion such objects moving through the galaxy at any given moment. Our solar system occupies a volume of space that intersects the paths of many of them over time. The vast majority are too small and dark to ever detect. But the population is enormous. The implications of that number reach in every direction. If 1 trillion interstellar objects are circulating through the galaxy, many of them carry chemistry from solar systems across billions of years of history, water from systems that no longer exist, carbon compounds assembled around stars that burned out before life on Earth began, silicates from rocky planets orbiting stars in the galactic bulge. Every interstellar object that passes through is a sample, a package of data about a world humans cannot visit, cannot observe directly, and in many cases cannot even locate. Reading those packages is the closest thing to galactic archaeology that currently exists. The 3 visitors detected so far are not an ending. They are the start of a catalogue that will grow as survey technology improves. Each new entry will add another piece of chemistry from another corner of the galaxy, another clue about how common the ingredients of life are, another signal from a solar system too far away to reach. The comet that arrived in 2025 is already gone, moving outward at 152,000 miles per hour, heading toward darkness that will hold it for longer than the Earth has existed. But it left something behind: data, questions, and a clear statement from the universe that we are surrounded by messengers from other worlds. We just had to learn to read them.